All three kinds of AWS load balancers use connection draining, which involves a deregistration delay. No praise for idleness. An AWS load balancer can certainly allow connections to drain. It will hold a connection open to allow any requests to receive their responses rather than abruptly shutting off the connection. But this should lead you to believe that load balancers favour some principles such as always tend to keep connections open. Well, load balancers are not pushovers. If a connection is open and it is not being used for requests and responses, it will be closed. The load balancer cannot tolerate idleness. You can configure an amount of time in seconds for your load balancer. This period of time is how many seconds of silence the load balancer is willing to endure before closing connections, and that period of time is known as the idle timeout. What kind of targets can each load balancer have? We know that with the classic load balancer, you were offered EC2 instances to choose from when selecting targets. We can see this on the screenshot below, which shows the console in 2012, 4 years before the ALB came in 2016. So you are given a screen where you can tick a box to bring in the EC2 instances so that they are under the control of the load balancer. Now, why is this important? Well, EC2 instances, the fact that they're the target, they can in fact have multiple ENIs, EC2 instances, elastic network interfaces. It's ENIs which are the bearer of IP addresses. These network interfaces are called elastic because they're portable. They can be moved from one EC2 instance to the other. Well, if the ENI is the bearer of the IP address and the ENI can be moved about, then it follows that EC2 instances can change their IP address. Suddenly, it becomes significant that the mapping shown in the image above is a mapping to a particular EC2 instance, identified by some code such as I-BC42F9E8, usually called the instance ID. Suddenly you realise that when your friend who wants one mastermind because his specialist subject was the AWS Classic Load Balancer, when he tells you that its targets are EC2 instances, this really isn't a shorthand for saying the targets are IP addresses. He really does mean EC2 instances. And EC2 instances can have multiple ENIs. If there was some situation in which you had to terminate instances and spin up new ones and make the new instances be the targets, you would have to go into your CLB and change the targets. So it was significant when in 2017, AWS announced that now the target of the load balancer could be specified as an IP address. They point out some interesting benefits to this. So here's the announcement. Elastic Load Balancing Network Load Balancer now supports load balancing to IP addresses as targets for AWS and on-premises resources. We're pleased to announce that network load balancers can now distribute traffic to AWS resources using their IP addresses as targets, in addition to the instance IDs. You can now also load balance to resources in on-premises locations reachable over AWS Direct Connect and resources in EC2 Classic. Load balancing across AWS and on-premises resources using the same load balancer makes it easy for you to migrate to cloud, burst to cloud, or fail over to the cloud, having that cloud as a backup ready to step in emergencies. Prior to this launch, when using an instance ID as a target, an EC2 instance could only receive traffic from the load balancer on its primary IP address and primary network interface. This limits hosting multiple applications on the same instance, where each application requires a different IP address, network interface, or security group. Using IP addresses as targets removes this limitation, as the load balancer can route to multiple IP addresses and network interfaces on the same EC2 instance. Load balancing using IP addresses also provides flexibility with microservice-based architectures, where each application target can now use a known port instead of a random port, simplifying inter-application communication. This feature also enables load balancing to your on-premises resources, thereby supporting hybrid architectures. Here's Jeff Barr's blog post. New application load balancing via IP addresses to AWS and on-premises resources. I told you about the new application load balancer last year, 2016 that was, and showed you how to use it to implement Layer 7 routing or application routing to EC2 instances and to microservices running in containers. Some of our customers are building hybrid applications as part of a longer-term move to AWS. These customers have told us that they'd like to use a single application load balancer to spread traffic across a combination of existing on-premises resources and new resources running in the AWS cloud. Other customers would like to spread traffic to web or database servers that are scattered across 2 or more VPCs, or host multiple services on the same instance with distinct IP addresses, but a common port number, and to offer support for IP-based virtual hosting. And he goes on. The point is, we had this announcement that meant that the NLB could now have IP addresses as targets, and that was beneficial. And you'll notice that ports were mentioned as well. So in the announcement, it said that there's flexibility if we use IP addresses. Each application target, I'm quoting, can now use a known port instead of a random port, simplifying inter-application, between application, communication. So there's something about using microservices which means that it would be beneficial if, when we're specifying our target, we specify the port that that we have to go through and use to get to that target. And it looks like in this announcement, it wasn't just that we can now have IP addresses as targets, but even though we'd already had always had a port specified, that port could now be a known port. So there are some port numbers that you'll see again and again. It's not just the case that there's a random number each time. The port number 80 is usually associated with HTTP, 443 is associated with HTTPS, and so on. And so that's what we mean by known port numbers. The boundaries of requests. Where does one request end and another begin? This is a very important question if we are sending multiple requests over one connection. After all, HTTP is a stateless request-response protocol that operates by exchanging messages across a reliable transport or session layer connection. With some help from James Kettle, let me explain how we signal to a server that one request has ended and another begun. Below we can see an HTTP request message. You can see that on the top line of a request, usually we say what protocol are we using. Here it's version 1.1 of HTTP. And you can see that we've printed that twice. It's here at the top and here at the bottom as well, which indicates that we're looking at parts of 2 requests. It says host:example.com, content length :6, content length :5. This here is a header. The word or the term before the colon is called a header, or the name of the header. Okay, it would be more specific to call it the name of the header, because the thing after the colon is also in a way part of the header. It's the value of the header. So we have the value of the content length header being 6 and then 5. Each request also has a method if you're talking about HTTP, which just means what is that request trying to do. These are categories which were set out in the instruction manual for how HTTP works. We've got post, get, put. So post and put are like they sound. You're posting data in, putting data in. Get is retrieving information. But here it's post. So the first part of the request is just stating that method, post, and then / and then HTTP /1.1. here it says 1234G post /HTTP/1.1. You can see a number of headers. What is a header? It's easier to show than explain. It's a name-value pair separated by a colon. Each header field consists of a case-insensitive field name followed by a colon, optional leading whitespace, the field value, and optional trailing whitespace if you want. That's RFC 7230. Kettle explains how, since HTTP version 1.1, there's been widespread support for sending multiple HTTP requests over a single underlying TCP or SSL/TLS socket. So TCP, that layer 4 protocol, transmission control protocol that Vint Cerf works on, and then SSL, secure sockets layer, /TLS. TLS, the modern version of it, transport layer security. The protocol is extremely simple. HTTP requests are simply placed back to back, and the server parses the headers to work out where each one ends and the next one starts. So when we use requests that are HTTP requests over a connection, it's a bit like squeezing out spaghetti out of a spaghetti making machine. It just pushes out, and we actually rely on someone there with a knife to sort of mark the boundary of where one request ends and the other begins. We need some marking or boundary to separate one request from another. In practical terms, there's a header whose name is content length. So look for a line like this. This header field is a way of communicating where one request ends and another begins. Servers are different though. Sometimes they differ in the way they interpret a single request. Kettle gives us an example involving a request being passed from a front-end server to a back-end server. The front-end server counts requests as large. Why? Because it prioritizes content length :6. Meanwhile, the back-end server in fact prioritizes a different header, content length :5. Suppose that both these headers are within the request that goes to the front-end server. Notice how the back-end is going to regard only a subset of the message as being the whole message. Again, the back-end is going to regard a subset of the message as being the whole message, meaning it's not going to read the message in its completeness. It's going to fail to appreciate all the parts of the message. This raises the question, what will the back-end server think about the leftover part? Because we've said the back-end is only going to look at a subset of the message, because the back-end server looks at content length 5, and 5 is smaller than 6. It thinks content length 5 is the really important one. It ignores content length 6, and 6 is the bigger one, the larger one. This raises the question, what will the back-end server think about the leftover part? Well, the leftover part will be considered the first part of the next message. And so the leftovers will basically spoil the next message. So just to recap, we have the front-end server, which has fantastically broad limits when it comes to marking the limits on where one request ends and one begins. And the back-end server is bitchy with narrow limits on what counts as a message. Look, it might make more sense to look at an example. So look at this request message. Post, we always begin with the method. HTTP 1.1, we've got those two content length headers, which is problematic because there's now opportunity for different interpretations about which one we should defer to, which one we should say is the actual winning one. And you can see this is a second request beginning here because it says post and we've got the version of the protocol. But of course it says 1, 2, 3, 4, 5 in blue, and then we have a G in red, and then we have post. So it's not really just post at the beginning of the next request, but 1, 2, 3, 4, 5, G post. we can imagine a situation in which the front-end server prioritizes content length 6, front-end fantastically broad, limits. This means that 12345G gets passed along. Thus, the front-end server draws back fantastically broad limits. However, the back-end server prioritizes content length 5. This means that it only regards the message to be 12345 and not 12345G, the 6th character. Now, of course, front-end server gave all the material to the back-end server. So, what does the back-end server do with the scraps, the G? Because the back-end server thinks that it's 12345, end. Forget the G. But what does the back-end server do with the G? The answer is that it prepends it to the next request. It considers the G to be part of the next request. The next request is therefore spoiled. The green text in the image above represents the next request which got spoiled. And you can remember we put the G in red, but then it was post in green and the slash in green and HTTP in green. So the green is the true next message. But of course, the problem is the servers don't see exactly what is green. And we're saying that server 2 thinks that there is a request which says G post. Kettle writes, under the hood, the front end forwards the blue and orange data to the back end. So the numbers were in blue, 1, 2, 3, 4, 5, and remember the G was in red or orange. The back end only reads the blue content before issuing a response. It thinks that one request ended with 1, 2, 3, 4, 5. This leaves the back-end socket poisoned with the orange data, the red G. When the legitimate green request arrives, it ends up appended onto the orange content, the red G, causing an unexpected response. In this example, the injected G will corrupt the green user's request, and they will probably get a response along the lines of unknown method gpost. The question, of course, is why one server prioritizes one header and another server prioritizes a different one. Desynchronization. If there is disagreement between servers in the way a message has been parsed, the servers are no longer in sync. They've been desynchronized. Therefore, attacks which rely on making servers desynchronized, they're called desynchronization attacks or desync attacks. And there are different types. I don't know if this is correct, but I think there are various kinds, with response splitting being just one of them. We've also got request smuggling, and these two forms of attack are mentioned in the specification for HTTP 1.1, which is RFC 27230. Now, it never uses the term desync in that RFC. James Kettle says that HTTP request smuggling was first documented in 2005 by Watchfire. Barracuda, the cybersecurity company, wrote an article following the research conducted by Kettle in 2019. It explains that the typical way cybercriminals execute these attacks is by sending the content length and the transfer encoding headers in the same request. According to the RFCs, this combination should be treated by prioritizing the transfer encodings headers value. However, the trick is to camouflage the transfer encoding header by introducing non-ASCII characters in the name, so the HTTP parser ignores that header. So it's an indirect technique used by attackers. We do something to one thing so that there's a sort of overflow, and the ultimate aim is to spoil the transfer encoding header so that we then have to move to a different header, and it's that shift to the next header in line, almost like shifting to the next person in line for the throne or something like that. Exploiting the known procedure that gets used. In terms of who we defer to, which header has priority. AWS announced a feature for the CLB and ALB called Desync Mitigation Mode. The announcement explains that one way to deal with disagreement is to come down on one interpretation. So we'll only accept requests that conform to RFC 7230. So in other words, an option to mitigate desync is to only allow requests that strictly conform to RFC. So the request of comments. This simply won't work in practice though. The fact is that a lot which is good does not conform to RFC 7230. A large percentage of real-world requests include characters that don't strictly conform to RFC 7230. This means that a strategy of only accepting requests which conform to it is not feasible. The solution seems to be to draw on a shared knowledge pool. The load balancer will classify every request based on its threat level using an AWS open source library called HTTP Desync Guardian. So, if you enable desync mitigation mode on your AWS load balancer, the load balancer will draw on knowledge from an open source library. This will more accurately categorize requests as threats or not threats. It will certainly be more accurate than simply allowing requests which conform to RFC 7230. If you put your load balancer in desync mitigation mode, you've 3 options. You can choose defensive, strictest, or monitor. The mode you most likely want is defensive. So HTTP Desync Guardian, a library for analysing and classifying your HTTP/1 point something, doesn't have to be 1.1 then, but your HTTP requests, to provide customers security balanced with necessity, to serve traffic for legacy or proprietary systems, which are not always RFC compliant. These are 4 categories: compliant, acceptable, ambiguous, severe. Well, if it's severe, it is either malformed or likely crafted to trick HTTP parsers and cause desynchronization. That's severe. But it might be ambiguous. Something is ambiguous if it has multiple meanings. Requests that might be treated differently by different HTTP servers and therefore may lead to desync issues. They may have request splitting and request smuggling as a possible consequence. That's the ambiguous category. These are categories which we put requests into. And then there's 2 good categories, compliant and acceptable. If it's compliant, that's ideal. It's an RFC compliant request, but it's more likely to be acceptable. It's not compliant, but it does not represent a security risk. Remember, a request is not problematic because it cannot be interpreted by a server. To be problematic, a request needs to be capable of being interpreted in different ways. It needs to be capable of that. Desync occurs not when requests are invalid, or not necessarily at least, but when they're ambiguous. Desync mitigation mode is something which you can enable on your load balancer. It's even a feature available on your classic load balancer. Recall that there were 8 configurable features on that, and we said that they could be remembered by CCC PSDTD. We looked at proxy protocol. Willie Tarot helped come up with that. He did come up with that in 2010, and it does not operate at layer 7 like the flaps of the apps of the squid, the X-forwarded form. So that's what the P is in that acronym, proxy protocol. And they're both those things, proxy protocol and the X-forwarded for header, are all about answering that question, who sent you? To investigate the origins of that X-forwarded for header, we looked at the Harvest project, which had its roots in the city of Boulder in Colorado. And in the housing policy there, in that city, we saw our first glimpse of rules governing rules. Incidentally, the concept of the city has been helpful for those architecting VPC environments. In 2021, Marwan Al-Shawi wrote a blog post entitled "Use a City Planning Analogy to Visualize and Create Your Cloud Architecture." We're told that the structure of a city can be thought of at 3 levels. There is the overall city architecture at the top. Within this, you have a number of districts, such as an education district and a financial district. Finally, there are a number of questions over the design of individual buildings. Why might people react badly to an article such as this one? I think it's because people are often suspicious when an extended analogy is made. An analogy is the comparison of two things. Let's suppose we call the first thing the unknown entity and the second the known or familiar entity. An analogy, or they're sometimes called analogues, an analogy breaks down the unknown entity into a number of features. Anabolism is breaking down food molecules in our gut. Then we reason that because some of these features are shared by the unknown and the familiar entity, other features must be shared as well. With an analogy, you are making a point or reasoning. Logos analogi. People are suspicious of analogies because we suspect that the expert could have matched the unknown entity with pretty much anything. That was his capability. We can imagine somebody saying that writing a great blog post is like eating a banana. It must have a great introduction. You can peel back the skin of a banana. Then there must be a consistent flow of information, chomping through the consistent flesh of a banana. A banana has occasional seeds of insight, and there should be seeds of insight in a blog post. We have to politely smile while we listen to this twaddle. So here we have two entities, the two circles. One is unknown and one is known. We point out that the known object consists of a number of features. These are the shapes, the yellow triangle, the circle and the red square, the green circle and the red square, that is. And we show that some of these features, for example, the yellow triangle and the green circle, are in the unknown object as well. And what we do is we then, with an analogy, is we then proceed to argue that because the familiar object also has this feature, which is the red square, we can conclude that the unknown object will have the red square. Or we can make it easier to see that as well as the yellow and green shape, the red shape is present in the unknown object. So that's the mechanism by which an analogy works. So the magic happens when features of the familiar object can start to justifiably be seen in that unknown object. That's the red arrow. So the choice of a banana is suspected to be arbitrary, though that's when an analogy goes wrong, or isn't adopted or taken up, or isn't persuasive of the minds of students. It doesn't persuade students of the conclusion that it ought to. Similarly, the choice of a city appears to be arbitrary, just like the choice of a banana was, meaning not governed by rules, arbitrary. Could we just as easily be talking about designing a house, designing a home office, the arrangement of Sunday brunch on a plate? There's a second cause for suspicion. We do not know whether the comparison is to bananas specifically or fruit. We don't know the generality of the category which we're supposed to be comparing it to, the unknown thing too. Perhaps banana is simply an example of a living organism. Perhaps it's that wide. And there are endless of lists of these working out questions which the analogy demands. All this working out has to be done before the student can take any real understanding from it. And this, I think, is why people react badly to an article that proposes that we think of architecting a VPC as analogous to planning a city. There are, after all, no reasons given in the article for adopting the analogy. I've no idea what planning a city involves because I've never planned a city, and I don't see any reason why those who became solutions architects in the IT industry will have planned cities. So how is it even possible for me to think of architecting a VPC as planning a city? Here's why it might be good for somebody to propose an analogy between a cloud architecture and a city. Organising a cloud architecture can be extremely overwhelming. This means it's advantageous to break the task into smaller parts. This itself reduces the extent to which the task is overwhelming. The threefold distinction, the overall city architecture, the districts, and then the streets, also allows a degree of flexibility. There are 3 broad categories, and tasks within each category can probably be done in any order. The city analogy is therefore helpful because it provides a loose structure which shows a way forward to those who feel overwhelmed. Now, it may well be that the choice of the city is somewhat arbitrary. This does not necessarily detract from the utility of the analogy. The major point is that you settle upon something to coordinate your planning of a large architecture. And this sort of arbitrariness is found in some legal rules. In the USA, it's the law that you drive on the right-hand side of the road. It's conceivable that the law instead asks citizens to drive on the left-hand side. In fact, in England, we drive on the left-hand side, so this law is somewhat arbitrary. What is important is that we settle upon something. Whether a legal system dictates that you drive on the left-hand side or the right-hand side, a side must be chosen. This allows all the citizens to coordinate their activity, avoiding crashing into one another. A similar thing may be occurring when we draw an analogy between a cloud architecture and a city. Arbitrary as the city may be, by trying to make the analogy work, we ensure we're aiming for some sort of structure. I'm sure many cloud environments have been chaotically enacted, with absolutely no foresight whatsoever. Maybe we could have drawn an analogy with planning a house, or planning a living room, or planning a town, or planning the layout of a Christmas meal on a table. Sunday brunch. The message is simple though. Plan rather than not planning. Despite being somewhat arbitrary in this way, the fact is that most people do know how cities work. There is thus a hierarchy that can be drawn upon. Everyone knows that London has a financial district and the West End and so on. We know that these consist of streets and that streets essentially function as containers for various buildings. There's buildings within a street, when we come to mail addresses at least. There's therefore a ubiquitous language which everyone already understands. If I say, now I'm implementing the buildings while implementing a cloud architecture, you can conclude that we're dealing at a very specific level. If I say I'm mapping out the districts, you can conclude that some higher level things have been sorted out. But there are still specific things to be arranged, and these conclusions you make, they all depend on the background knowledge about actual cities. So basic terms relating to cities form a sort of ubiquitous language. Al-Shawi's article is therefore worth a read.